Hi student, good morning. Today we are going to talk about 12th standard physics, lesson number 4, electromagnetic induction and alternating current. Part 2 class. In this session, we are going to discuss motional EMF from magnetic Lorentz force and eddy currents, application of eddy currents. Now go to start with motional EMF from Lorentz force. Now tell me students, what is motional EMF? So this is the EMF produced due to the motion of the conductor in a uniform magnetic field is called a motional EMF. EMF is produced due to motion of the conductor in a uniform magnetic field is called a motional EMF. So students, here we are consider the magnetic field. The cross is represented. So this is a cross is represent presence of magnetic field, and a magnetic field lines is perpendicular to the inward direction, perpendicular to the plane of the paper. This is a plane of the paper, act in inward direction. Magnetic field is perpendicular to the field acting in inward direction. In this magnetic field, we are having a conductor. This is a conductor AB of length of L. This conductor is moved with velocity V. Now understand students, this conductor is moved with the velocity V. V is nothing but velocity, moving in this magnetic field. When they move with the conductor in velocity V, all the free electrons in the conductor and also moving with the velocity V. So already we have seen that when a charge moves in a magnetic field, it will experience magnetic Lorentz force. It will experience magnetic Lorentz force. This magnetic Lorentz force is given by, this is nothing but the Lorentz force act free electron in the direction of B to A. So this is a capital A, B to A, and is given by a relation. What is relation? Already you studied about third lesson, magnetic Lorentz force. FB. B is a represented magnetic field. This is a magnetic Lorentz force. F vector is equal to charge E minus E into V vector. Velocity is represented into B vector. Magnetic field is constant. Understand? Okay. Then due to the magnetic Lorentz force, what will happen? Now see the magnetic Lorentz force, what will happen? When the conductor move with the velocity V, every electron experience this much of free electrons, this much of force, this much of force. Due to this force, all the electron will flow in the one direction. All the electron will flow in the one direction. So EMF is produced. That is a induced EMF is produced. Because of the induced EMF, there is flow of current. Flow of current. So students, now see, already you know that magnetic field acting in inward direction. Now current is produced. That means induced current produced. Because of the induced EMF, there is flow of current. So all the electron flow in the one direction and they giving to accumulate at end B. all the electron flow in the one direction and giving to accumulate at end B. So end A of this conductor will have large accumulate of electrons. So because of this flow of current, this conductor, an electric field is produced. This is a electric field. Electric field is produced on the conductor. So this electrical force, because of electric field, we know when a charge kept in a electric field, it will experience a force. Understand, students? So because of electric field, we know that when a charge kept in a electric field, it will experience a force. This electrical force is given by F vector is equal to E is nothing but represent electrical field. A force F vector is equal to minus E into E vector. So because of electric force, all the electron flow in the one direction brings to accumulate at a end A. Now see the diagram. The electric force, all the electron flow in the one direction bring to accumulate at end A. So end A becomes more negative. Now see, at the end more negatives. This is a more negative, and end B becomes more positive. Because of this separation of charges, there is potential difference across the end. Now calculate potential difference across the end. So this electron will continue the move until and equilibrium condition is reached. So when the equilibrium condition is reached, the magnetic Lorentz force is equal to electric force. Now see, this is a magnetic Lorentz force and electric force, that is both are equal. Now FB vector, modulus of FB vector is nothing but magnitude form FB, that is equal to FE, magnetic field of force, electric field of force, both are equal. No more electron toward the end and make this A to be more negative. So under this condition, a potential difference is correct. Potential difference is correct. So the potential difference is correct. The potential difference of across X of the conductor is obtained by equating these two forces, electric force and magnetic force, that is minus E into V vector cross B vector, that is equal to minus E into E vector. Modulus of R, now write it magnitude form, is nothing but E into V vector cross B vector, that is equal to minus E into E vector. Okay. So here the magnetic field of velocity perpendicular to each other. Magnetic field or velocity is perpendicular to each other. Okay. When I write from this equation minus E VB sin, this is a perpendicular 90 degree, sin 90 degree, that is equal to minus E into E. Now minus E is cancelled. Now VB sin 90 is equal to E. What is the value of sin 90? That is equal to 1. Sin 90 becomes 1. So we'll have, write the equation VB is equal to E. VB is equal to E. So students, the potential difference between two ends of the rod. Already you know the formula, potential difference, electric field and potential difference. We know that V is equal to E into L. Therefore, V is a potential difference, that is equal to, what is a potential difference? Therefore, we know that E is equal to V by L, potential difference per length of the conductor. Now, this equation substitute here. V by L, that is equal to E. That is equal to E. Now, therefore, V is equal to potential difference, V is equal to velocity of the particle, magnetic field, that is length of the conductor, VBL. Already you studied this formula in third lesson, magnetic Lorentz force. Because of the motion of the conductor of magnetic field, in this potential difference is called a motional EMF. So the motional EMF can also be written as, this is called a motional EMF, can be also written as E is equal to BLV. E is equal to BLV. So students, this expression of motional EMF, since EMF arises due to the motion the conductor in a uniform magnetic field, this EMF is called a motional EMF. Are you clear? So this is EMF is produced due to the movement of the rod. It is often called a motional EMF. Then if the end A and B, that is length of the rod, A and B is a length of the rod, are connected by the external circuit, A and B connected to the external circuit, this length of the rod act as resistance. So total resistance of the conductor R. Then the current, what is the formula according to Ohm's law? Ohm's law is equal to I is equal to, what is potential difference by resistance of the conductor. Ohm's law. Okay, now substitute, what is the induced current? That is I is equal to, potential difference is nothing but induced EMF. Induced EMF E divided by resistance of the conductor. Already you know that induced EMF, that is equal to BLV, resistance of the conductor of AB R. So this current flow in the circuit, the direction of the current is found from right hand thumb rule. Already you know that right hand thumb rule. Now tell me once again, remaining Fleming right hand thumb rule. We can take a 3 finger, thumb finger and a middle finger, 4 finger. So these 3 finger mutually perpendicular to each other. So 4 finger point in the direction of magnetic field and the thumb in the direction of motion of the conductor. Then the middle finger will indicate the direction of induced current. So this is a important one. So sometimes ask 5 more questions. So students, understand. Next topic, it is very important one, eddy currents and application of eddy currents. So students, listen. Now tell me what is eddy current. So there is nothing but induced current in the form of eddies, like in the concentric circle. So this is a induced current like in the concentric circle, or this induced current flow through the circular path or only closed path. Understand students? Okay, now see, this is a induced current. Is nothing but we call it is eddy current. Okay, then first discovered by this eddy current Francois Avago in 1825. So is a greatest mathematician, France mathematician, and also 25th Prime Minister that country, France country. So students, he tell about this induced current introduce a new name, a rotatory magnetism. So after that, few years later, according to Faraday. So Faraday tell about law of electromagnetic induction. Now tell me what is meant by electromagnetic induction. It's nothing but produce induced current when changing magnetic flux linked with the coil of wire. Now understand, let us consider two coil C1 and C2. C1 coil we call it is primary coil. C2 coil we call it is secondary coil. Now C1 coil across connected to the battery. One end of the coil is connected to the positive terminal and another end of the coil is connected to the key and negative terminal of the battery. Now C2 coil across connected to the galvanometer. Galvanometer is nothing but measuring current. Okay, now primary circuit, now close the key, current flow through the C1 coil, that means primary current, and produced a magnetic field. This is a magnetic field, north pole of the magnetic field and the south pole of the magnetic field. Now again increasing the current and also magnetic field lines. This is a magnetic field lines are produced in large. So these magnetic field lines interact with the secondary coil and EMF is produced. So this is nothing but changing magnetic flux linked with the neighboring coil C2 and EMF is produced. This EMF is called induced EMF. This induced EMF flow through the closed circuit is called induced current. So this current deflected galvanometer. This is a deflecting galvanometer. So students, now tell me Faraday's law of induced current. So is equal to d phi b divided by dt. What is phi b? This is nothing but magnetic flux. So magnetic flux changing with respect to time. When changing magnetic flux linked with the coil or closed circuit. So induced EMF, induced current is produced. So okay, next go to find eddy currents or Foucault current, sometimes as Foucault current. So students, Leon Foucault in 1855 started 1855 for electromagnetic induction take place. It is not necessary to have circular coil or coil of wire. This electromagnetic induction can also take place in metal sheet. Now taking a metal sheet, the only difference is there if it is coil of wire. This induced current has specific path flow away, but when electromagnetic induction take place in a metal plate, the induced current do not have a specific path for its flow. So what will happen here? If electromagnetic induction take place in metal plate, the induced current flow in the circular path. This is a induced current flow in the circular path. That is, path of the induced current is similar to that of the eddies of water. Understand? Or any in the form of whirlpool. This current, which is shape of eddies, is called eddy current. Now listen student. Now taking the coil of wire across connected to the AC source. Now AC current flow through the coil and produce a magnetic field. This is a magnetic field lines. So these magnetic field lines interact with the metal plate. Now see, this is a magnetic field interact with the metal plate and produce the eddy current. This is nothing but eddy current. Understand? Okay. So this eddy current always flow as above the cause according to Lenz's law. What is Lenz's law? Oppose the cause that produced because of magnetic field and eddy current act in a opposite in direction. So Lenz's law is given by, now see, this is a Lenz's law is given by E is equal to minus d phi by dt. Magnetic flux, so the negative sign indicated by oppose the cause that. Are you clear? Okay. Sometime ask two more question. What are the eddy current? So this is a proper definition. When a mass of metal moves in a magnetic field, or when the magnetic field through the stationary mass of the metal is altered. Anyone, mass of the metal or magnetic field, anyone is altered. Induced current is produced in the metal. This induced current flow in the metal in the form of closed circuit. This is nothing but closed loop resembling eddies. So whirlpool. Hence this current is called eddy current. The direction of eddy current is given by Lenz's law. Understand students? Okay. Now let us see a simple demonstration to understand this eddy current. So we are having a magnet. This is a electromagnet. North pole of the magnet, south pole of the magnet. How to create a electromagnet? Now taking a metal sheet, a number of turns of the coil across connected to the battery. Now current flowing through the coil get a act a electromagnet. This is a acting a electromagnet. So they will act as electromagnet and current through the circuit. The magnetism, no more excitation. So now a pendulum is suspended. This is a metal plate. Is called a pendulum. Pendulum is an oscillate within the magnetic field. Between the magnetic field. Now let us consider flow of current. Now see students. Now here key is open. Now circuit is open. No current flow in the circuit. At the time the pole pieces of magnet not excited. So there is no presence of magnetic field. Here no magnetic field. So magnetic field is no, because of do not current flow in the circuit. So okay, then the pendulum is slightly displaced. Now see, the pendulum is slightly displaced and released. It begins to oscillate and it executes a large number of oscillation, more than oscillation before stopping, because of before stopping or come to rest. Now here air fraction is the only damping force. Understand? Okay. Then see second diagram. Now key is closed because of when the electromagnet is switched on. Now current flowing through the circuit and the disc of the pendulum is made to oscillate. Now here eddy current is produced. This eddy current acts in the direction so as to oppose the motion of the conductor. Where eddy current produced in the metal. So here this is the eddy current. Motion of the conductor oppose the motion of the conductor. And also strong damping force that the pendulum come to rest within the few oscillation. However, if some slot or cut, now see, this is some slot or cut or hole is drilled in the pendulum. This pendulum, disc of the pendulum, the effect of eddy current are reduced. Effect of eddy current are reduced. This is a current. Eddy current are reduced when the pendulum, disc of the pendulum now will execute several oscillation before come to rest. So students, this is a clear demonstration of eddy current. Okay. Then go to discuss how to minimize the eddy current. It is a very important one. One more question sometime asked. So student, now taking a metal plate, this is a metal plate, now passing through the current. What will happen? Here in the conductor get a heat. So student, the current is nothing but eddy current. Eddy current flow in the conductor, that means metal plate. Now here large number of energy is dissipated in the form of heat. So energy is converted to heat according to Joule's affecting current. So this energy lost due to the flow of eddy current is inevitable, but it can be reduced to greater extent with a suitable method. So students, eddy current, how to minimize? This is can be used to a laminated core. One type of eddy current as minimized. This is one type of minimized materials. So, and again armature. So insulator winding of an electric motor. Now first see insulated laminate of the core of a transformer. What is a laminate core of transformer? This is the laminated core for a single core of the lamination. So this lamination, number of lamination we attach it together a single form, that is this form of core of a transformer. So now see, this is the laminated core. Is nothing but a simple transformer core. Okay, then second one, armature. Insulated winding of electric motor. This is a armature. large number of copper wire, that means made up of insulator. So while for electric motor, winding is made up of group of wire or large number of wire insulated from one another. This insulation, what is uses? So does not allow the heavy eddy current to flow through the conductor. So hence losses are minimized. So now see, this is an electric motor. This is nothing but armature. This is copper coil. This one is a laminated core. So sometime ask 2 mark question. How to minimize the eddy current can be used to a laminated core and armature. Understand, students? Okay. Then go to very important problem and a simple problem. A spherical stone and a spherical metallic ball of same size and same mass are dropped from same height. Which one, a stone or metal ball, will reach the earth surface first? Which one is the reach the earth surface? Just tell me your answer. So students, now listen to it. Now taking two objects. This is a stone object and another one is metal object. Both of the object same mass and same size. Now drop from some height. Which one is the reach the ground? So now listen. The stone will reach the earth surface earlier than the metal ball because of your gravity force will be acting. Understand? Stone will reach the earth surface earlier than metal ball because of gravity force. No eddy current produced here, but a metal plate here surface of the earth. Already you know that earth has a magnet, act a magnet. Now magnetic field is produced interact with a metal ball. So can be relative motion between the metal ball and the magnetic field. Here induced current, that means eddy current is produced. So this eddy current oppose the cause that because of magnetic field and eddy current acting in the opposite in direction. So this is a slowly come to reach the earth. So this is a reason. The reason is that when the ball fall through the magnetic field of earth, the eddy current are produced in it which opposite motion. But in the case of stone, no eddy current are produced and fall freely. Understand, students? This is a very important 2 mark questions. Note it down. Okay, then go to discuss about application of eddy currents. So many application is there, but now going to discuss some application of eddy current. The first type of eddy current, application of eddy current, induction stove. Second one, eddy current brake. Third one, eddy current testing. And fourth one, electromagnetic damping. Now first application, induction stove. So students, already we are studied in second lesson electric device according to Joule's law of heating. So this condition also same thing, induction stove. What is uses of induction stove? This is nothing but used to cook as a food. So cooking purpose only. The induction stove, it is used to cooking purpose. So student, cook the food quickly and safely with less energy consumption. Note it down. quickly, food is quickly and safely with less energy consumption. Below the cooking zone, there is tightly wound up coil of insulated wire. Now listen to it. This is a below of cooking zone metal plate. So this is a coil, large number of winding. So made up of suitable wire like copper wire is placed over the cooking zone. When the stove is switched on, an alternating current flowing through the copper wire. Alternating current flowing through the coil produce high frequency alternating magnetic field. This is a high frequency magnetic field, alternating magnetic field which induced very strong eddy current. Induce the strong eddy current in the cooking pan. Now this induced current is nothing but eddy current interact with the pan, cooking pan. So heat energy. This eddy current amount of energy is converted to heat according to Joule's heating effect, which is used to cook the food. Now see, this is a copper, insulated copper wire. This is metal plate. Now the AC current, AC source is applied or flow through the coil, get heat is produced, this heat object. Here on the metal plate produced the eddy current. Understand? So this eddy current, the amount of energy is released is converted to heat energy. This heat energy flow through the cooking pan and used to cook the food. Understand? Okay. Then second application, eddy current brake. So there are two type of eddy current brake. One is a linear eddy current brake and another one is circular eddy current brake. So this eddy current braking system of train, so generally used a high speed train and a roller coaster. So now taking strong electromagnet are fixed just above the rail. Now listen to it. This is a strong electromagnet fixed above the rail to stop the train. When electromagnet are switched on, the magnetic field of this magnet induced a current. This magnetic field of the electromagnet induced the eddy current in the rail, which oppose or resist the movement of eddy current. So this is called a linear brake. Now see, this is a magnetic field interact with the metal plate. So now here induced current is produced. And the second type, circular eddy current. Circular eddy current brake. Now see, this is a circular disc. This is a electromagnet. Now rotating the disc, now come to close the electromagnet. So here magnetic field is produced interact with the disc. So this rotating disc slowly come to rest. So same thing. Now the wheel of the train, this is a train wheel, this is a electromagnet. Now relation between electromagnet and disc. Now here induced eddy current. So in the disc which stop the train. So this is a circular eddy current brake. Okay, then third application, eddy current testing. The same thing, eddy current. Now taking the coil, current is flow through the coil, magnetic field is produced, interact with the metal plate and produce the eddy current. So now see, this is a magnetic coil, AC source, magnetic field lines. This is a circular path in the eddy current. eddy current magnetic field. So conductive material. This means metal plate. Now see, this is a type of device. Many type is there, but this is a one of the type of eddy current testing. So what is the uses of this device? Now listen. It is one of the simple non-destructive testing method to find defect like surface cracks, air bubble present in the specimen. Say for example, underground cable wire. Sometime some fault, wire are cut, so interaction between the two wire. Sometimes some problem is there. How to find out? Can be using eddy current testing. Understand, students? Okay. So the coil of insulated wire is given in alternating. The same concept. So this is a coil of wire. The alternating current flow through the coil of wire. Now here produce the alternating magnetic field. This magnetic field interact with the surface. When this coil is brought near the test surface, the presence of defect cause the change in phase and amplitude of the eddy current. Something change amplitude of eddy current that can be detected by some other means. So this way method, a defect present in the specimen are identified. So this is nothing but eddy current testing. And fourth one, electromagnetic damping. So student, now taking a galvanometer, armature of galvanometer, coil is wound on this soft iron core. This is a soft iron core, laminated sheet. That means large number of copper wire made up of insulator are winding. Once the armature is deflected, when the relative motion between the soft iron core and the radial magnetic field induced eddy current. This is a radial magnetic. So now taking osteomagnet. This is a soft iron core. Relation between magnetic field and a soft iron core, which produces a radial magnetic field. This radial magnetic field induces the eddy current in the cylinder. The damping force due to flow of eddy current bring the armature to arrest immediately and then galvanometer so steady deflection. This is called electromagnetic damping. Okay students, I think hope you understood. Tell me your answer, my questions. How is eddy current produced? How do they flow in a conductor? The second question, mention the way of producing induced EMF. Third question, obtain an expression for motional EMF from Lorentz force. This is a very important one. Using Faraday's law of electromagnetic induction, derive an equation for motional EMF. And the last question, give the uses of focal current.